Okay, so let me start by thanking the organizers. I'll talk about extreme statistics in 1D Coulomb gas, and this is done in collaboration with Abhishek, Satya, Sanjeev, and Gregory. Okay, so universality. So this is a concept, common concept that we find in statistical physics in basic courses in statistical physics, like in phase transitions. But there are other simpler and widely known contexts where you see this concept. For example, central limit theorem, where you consider, say, n independent and identically distributed random variables chosen from some distribution with, say, finite moments, at least the first two moments, and you look at the sum of n such variables, and in the n going to infinite limit, you find that that sum, after proper shifting and scaling, the distribution of that quantity converges to a limiting distribution which is n independent, and that distribution is Gaussian irrespective of px. So that's a notion of universality. So the similar universality also appears in another context which is called extreme value statistics. And once again, you consider in IID variables, and this time you look at the maximum of these variables. And again, in the large n limit, you are interested in the distribution of that maximum. And you find that after some proper independent shifting and scaling, the distribution of that quantity can be described by some independent limiting distribution or scaling distributions. And it turns out that there are only three possible types of that distribution, which are called the universal scaling functions, depending on the tails of the parent distribution Px. So the question, let me show you the distribution, these three types. These are Gumbel, Frechet, and Weibull. I'm not going to the details of this. So the question is if these distributions are strongly, these variables are strongly correlated. So precisely if you are given the joint distribution of these variables, and what can you say about the distribution of the maximum of these variables? So this question was studied in the context of random matrix theory, where you usually consider n cross 1 matrix where the elements are random and chosen from Gaussian distributions, such that the joint distribution is given by this, which are invariant under some rotations, and you are interested in the spectral statistics, like the joint distribution of the eigenvalues of this matrix. And the answer to this question was given at least for these Gaussian ensembles by Wigner in 1951, and he got this elegant formula for this joint distribution. And where beta is the Dyson index, which takes values 1, 2, and 4 for different ensembles. So this distribution has a very interesting interpretation. Dyson, due to Dyson in 1962, he says that, look, this distribution looks like a Boltzmann distribution of n charges which are living on one-dimensional line and confined by a harmonic potential. However, they're interacting via 2D logarithmic Coulomb interaction. Okay, so in this picture, the lambda max, which is the largest eigenvalue, is basically the position of the rightmost particle of this gas. This is called the Coulomb gas or the log gas. I'll refer to that as log gas in the later part of my talk. Okay, so you ask what is the average density, or the typically what will be the particles, what will be the density of these particles. And it turns out that, so basically it is defined by this, and you take the average of this quantity over this distribution. It turns out that this charge is actually settled down over a finite region because of this two opposing effects. This guy is trying to pull them near the center, whereas this guy is trying to push them apart. And they settle down over a finite region, and the density is in the large limit converges to an n-independent function, which is called the Wigner semicircular law. That we know, many of us know probably. And of course, from this, you can easily see that the lambda max, which is the maximum eigenvalue or the maximum position of the rightmost particle, will sit on an average at the edge of this density, and which is square root 2. So this is not independent because I have taken scale variables. And if you look at the gaps between particles at the edge of this density, it turns out that the typical gaps are of order n to the minus 2/3. So the lambda max will fluctuate around this mean value, and the typical fluctuations will be of order n to the minus 2/3. And you are interested in the distribution of these typical fluctuations. And this distribution was computed by these two gentlemen, Harold Whittam and Craig Tracy, in 1994. And they showed that this distribution indeed after proper shifting and scaling is described by an limiting distribution which is now known as decision distribution, and that distribution is given by the solutions of Parleve 2 equations. For example, for beta equal to 2, this is an explicit expression. The distribution is given by the solution of this equation with proper boundary condition. With this boundary condition, the solutions are called the Hastings-Macleod solutions. So these distributions are usually asymmetric in the sense that their asymptotic behaviors are different. In the left side, it decays as exponential of minus mod z cube, whereas on the right side, it decays slower because it's minus 3 by 2. So this distribution describes a typical fluctuation and appears in different seemingly unrelated problems. For example, in Coulomb problem of long-lasting using subsequence, in KPG problems, in height fluctuations, in non-interacting Brownian motions, interacting fermions problems, financial performance. Also, people have observed these distributions in experiments in liquid crystals or in coupled laser experiences. So these are nice popular science articles where you can read about this ubiquity of Tessier-Ulam distributions. So in that sense, this distribution looks like an universal distribution, but there is another universal aspect which is the following. Remember that this distribution was derived originally by considering the particles in an harmonic potential, but it turns out that if you change this harmonic potential by some another potential which is sufficiently confining, then also the charges will settle down over a finite region, and as long as this density goes to 0 at the boundary, at the edge, obeying the square root behavior, then it turns out that the distribution of the typical fluctuation of the lambda max around this mean value is again described by the Tessier-Ulam distribution. So the question now is that instead of changing the potential of the confining, keep that as harmonic, but you change the interaction among the particles, which was logarithmic to start with. If you change now, will the lambda max, the typical fluctuation of lambda max be described by Tessier-Ulam distribution? So what would be the natural choice for the interaction? See, the particles are anyway living in one dimension. So it's better that let's consider the actual 1D Coulomb interaction, which is linear, non-logarithmic. And we consider this model, and I ask this question that what is the distribution of the typical fluctuation of the position of the rightmost particle. And this model is a paradigmatic model for the 1D plasma because one can compute various bulk properties, and people have studied this model in 1960s and computed various bulk properties. But here we look at the extreme value, the statistics of the age properties. Okay, so let me tell you the answer of this question, that the distribution of this X max for this interaction is not given by the Tessier-Ulam distribution. Okay, so here also the charges, because of these opposite effects, will again settle down over a finite region, and in this case it's minus 2 alpha to alpha. Alpha is the strength of the interaction, which is a parameter sitting in front of the interaction. And but in contrast to the log gas case, here the charge density is just flat. As a result, the gap between any two particles is like of order 1 over n. And as usual, the lambda max or the X max average on an average will sit at the edge, and they'll fluctuate on typically on a scale of order 1 over n. In contrast to the log gas, where it is the typical fluctuations of order n to the minus 2/3. And we find that the distribution on this scale is given again after proper shifting and scaling by a function, by a distribution which is computed from another differential equation which is non-local, and it's a kind of eigenvalue equation. It's non-local but linear. This is a kind of a cumulative probability, which if you look at in comparison with the log gas case, where this distribution was also computed from a solution of a differential equation, and that differential equation was Parleve 2 equation, which was local but non-linear equation. Okay, so I do not have much time to go into the details of the derivation of these things, but however, I would like to say that, okay, you start with the writing the partition function of this model, and then you can map this model to a, this interaction was a long-range interaction. Sorry, I can do that. A long-range interaction, but you can map it to a short-range interaction, and then you can do some calculation and find out this relation. Okay, so this is a plot of that distribution, and we compare that with the numerical simulation, and we see it matches nicely. And this distribution also has asymmetric asymptotics. This distribution on the left hand side decays as e to the power minus mod x cube as in the distribution. However, on the right hand side, it decays as e to the power minus x square by 2, in contrast to the residual distribution, in which case it decays as e to the power minus x to the power 3 by 2. Okay. So these functions actually describes the typical fluctuations around the mean, which are of order 1 over n in this case, and in the log gas case is of order 1 over n to the 2/3, but they do not describe the atypical fluctuations, like the fluctuations of order 1 from this mean point. And those descriptions, those fluctuations, it turns out that can be described by large deviation functions in this case. And it turns out that in this direction, which is inside the bulk, the large deviation function, the probability decays much faster as e to the power minus n cube, the speed is n to the power 3, and with a modulated by a large deviation function. Whereas on the other side, it decays as e to the power minus n square and modulated by a function. This n cube and n square can be understood from physical arguments. N cube comes from the energy scale of moving one particle in this direction, whereas n square comes from the energy scale by pulling one particle in this direction. So we compute these functions also explicitly, and we find that the phi minus has a cubic behavior if you go from as a distance from this point, whereas phi plus has a quadratic behavior. And from this, if you compute, if you define a free energy like quantity, which is minus log of qn by n cube, and take the n going to infinite limit, you get a free energy kind of quantity, which has a discontinuity in a third order derivative, and you can associate to a third order phase transition. Okay, so let me summarize. So with respect to changing the interaction among the particles in the distribution of x max cannot be described by a Tessier distribution. At least for 1D Coulomb gas case, it is different, and it has similar large deviation functions. And it turns out for this particular case that this function is very interesting, that it can describe various other quantities. For example, index, which counts the number of particles on the positive side, and as well as the gap, which is the gap between the rightmost and the next rightmost particle. And also we are also interested in looking at other questions like general interactions connected to quantum systems and higher dimensions. And thank you.
Any questions?
Hi. So is the so you said that the width of the Tracy-Widom distribution is 1 by n or 1 by n to the 2/3?
1 by n to the 2/3.
Sorry?
1 by n to the power
2/3. Yeah. So in the large n limit, does the slope attain a singularity there?
Where?
In the large n limit,
Yes.
is the slope singular there?
Slope.
Or does it smoothen out? No, so the Tracy-Widom part disappears with increasing n, right?
Yeah, but you zoom into that region and then look at the typical fluctuations, right?
Yeah. No, so with increasing n.
Is Tessier distribution. Yeah, I mean, if you divide the cumulative probability by n, then in that case, this becomes a point. And that actually in a finite system, that function acts like a crossover between two large deviation functions.
Okay, so the slope is singular there.
Slope, I don't understand what slope.
The left tail and the right tail have different slopes, right?
Yeah, because that becomes,
Okay.
It has a discontinuity.
Okay.
Yes.
So this function that you found, this f alpha, whatever, can it be described in terms of special functions, known special functions in any natural way?
That we don't know because we couldn't solve that equation for any arbitrary alpha.
But then you plotted exact versus numeric. So what?
That means the solving that equation numerically.
I see.
And the other one is the Monte Carlo simulation.
I see. Okay. But you don't have an explicit expression.
For arbitrary alpha, we don't. But for different, alpha going to 0 and alpha going to infinity, we have some expressions.
I see. Okay.
But for arbitrary
But any finite non-zero alpha, you don't have.
I don't know whether it's possible to find a solution of that equation. Okay. But we don't know.
Any other questions? Okay, if not, let's thank Anupam as well as all the speakers of this session.